very much for the introduction. Yeah, so, okay. Yes, so as Olga already introduced very well, we have a nice model for our universe. And this is also what I will be talking a bit about today. So in the big picture, we have something that starts with inflation and ends with recombination and the formation of CMB. But what I will focus on is this epoch in between, where we have neutrino decoupling, we have annihilation of electrons and positrons, and I'll very briefly mention nuclear synthesis as well. So if we start with neutrino decoupling takes place when the weak interaction rate becomes smaller than the Hubble expansion rate. I think we should close this window. Yes, and once the neutrinos decouple, what happens is that they stop scattering efficiently with electrons and positrons that are also present in the plasma in the early universe. So the next event, so to say, that I will discuss is electron-positron annihilation. It's not maybe the best name for this, but it's what most people use, so I will also use it. What actually happens is that electrons and positrons become non-relativistic, and for that reason, this equilibrium between electrons and positrons and photons is pushed towards the photons, since when photons do not have more than 500 keV, they cannot produce electrons and positrons anymore. And the third epoch that also falls within a quite narrow range of temperatures is nuclear synthesis, which is affected by both the content of neutrinos and also by ineffective, as Olga talked about previous today. Good. So one of the things that we can observe from the early universe is ineffective. And it basically parameterizes the energy density of radiation in this slightly funny way. The idea of defining it this way is that the naive standard model value is 3, and then we have these corrections, so we end up with a slightly higher value in reality, these 3.044. And I'll give you some more details of how we reach that number. What is important to remember is that this is something that we can determine based on cosmological observations, and the value is very close to 3 when we consider CMB and BBM and so on. So we know that there are about 3 neutrinos, and we cannot add extra particles to our model that would look like a 4th neutrino and be produced in the early universe. Good. So the budget for getting the correction is this one that we have seen already. And I'll start with giving a bit more details on the relativistic assumption here first. So the assumption that the electron mass is much, much, much lighter, smaller than the decoupling temperature of the neutrinos. The neutrinos decouple around 1 MeV. The electron mass is half an MeV. So obviously it's not a good approximation. And still, I mean, the correction is not huge, right? So it's also not a crazy approximation. Oh, wrong way. So if you remember how we got to understand the neutrino decoupling in the first place, the idea is to consider the entropy density here that you can calculate using quite simple formulas, energy density and pressure. And then you can compare the values before and after neutrino decoupling. And in the end, you get this ratio between the neutrino and the photon temperatures that you can predict with this number of assumptions. The first one being that electrons are basically massless at this temperature. So in order to relax that, we also need to look at entropy conservation. So we take two different scale factors. We take scale factor 1 and scale factor 2, and then we assume that electrons and photons are in one plasma and they conserve entropy. Neutrinos are in another plasma and they also conserve entropy, and then we can set up these two simple equations. Good. Then if we take the first scale factor to be at the temperature of neutrino decoupling, and the second one to be well after all electrons and positrons have disappeared, we can calculate the entropies. So there are some numerical factors, and then there are the number of degrees of freedom associated with each particle. And then we have this correction that is due to the finite electron mass. After electrons and positrons have disappeared, we only have the photons left. And for neutrinos, we do not have really much of a change. We have the same number of neutrinos both before and after electrons and positrons are, have disappeared. Good. So now the question is, what is this delta S? And it turns out it's actually quite easy to calculate. So you take the expression for the entropy density. It's this one in the top from Olga's slide here. And then you plug in, you plug in the energy here and the expression for the pressure, and you have an integral that you can calculate numerically, even quite easily. And you find a correction that is about minus 0.01 to the entropy density, and that can then be propagated to delta M effective, where you get a multiplicative factor of 3. So in the end, you get a bit more, and you get these 0.04. So that is really the main contribution to these 3.044 that people mention quite often. And I mean, this is a quite simple thing to understand. So the next thing is not quite as simple. It's finite temperature QED corrections that give the next corrections. And the idea here is that in the rough calculations, we are treating the system as an ideal gas. So electrons and photons do not interact. In reality, of course, they do interact quite a lot because we have electromagnetic interactions. And those interactions change both the energy density and the pressure through a number of different effects. So if we sort of look at the slightly more formal side of this, we can go back to statistical mechanics, and you might remember that there's something called a grand canonical partition function, maybe. And then you can calculate the different order corrections to this. So the 0th order is basically what corresponds to the ideal gas approximation. And once you have the grand canonical partition function, you can go on and calculate pressure, energy density, and entropy density from that. So what kind of effects do contribute to this? There's this two-loop diagram that contributes at 2nd order, and then already at 3rd order there's this sum of ring diagrams that also contribute. And to sort of get a feeling for what this is, I've taken the expression for the pressure here, and you can see it's slightly nasty, a slightly nasty expression, but on the other hand, it's something that you could take and put into a computer code and include in your calculations without too much trouble. Historically, there have been a different approach to including these finite temperature QED effects, and that is to use a quasi-particle picture. So instead of correcting the pressure and so on with these kind of formulas, you simply take your energy for photons and energy for electrons, and then you correct them by adding an effective mass to the energies. And this works quite well for transport equations. It does not work so well for bulk properties because there you get some double counting because it's not really a strictly correct way of doing it. This approach also cannot account for any kind of collective effects in the plasma. And the third order effect that I had on the previous slide is a collective effect. So intrinsically, this cannot work beyond the second order correction. So I would say that including the full expressions for pressure and so on are the better approach. Yes, and maybe I should mention also that in the end, if you include this second order QED corrections, then you get a correction of 0.01 to delta ineffective. So the next step in our trip through these different corrections is non-instantaneous decoupling. So except for the electron mass not being 0 at 1 MeV, there's also the effect that neutrinos continue to interact with electrons and positrons even at lower temperatures. So we have a momentum distribution. So the highest energy tail of that will continue to be coupled reasonably effectively to electrons and positrons also at lower temperatures. And the way to treat that is to get back to the very loved Boltzmann equation. Of course, you also have to include the evolution of the universe. So you have to solve the Friedmann equation and the continuity equation to get the evolution of the photon temperature, which describes how the electrons and positrons become Boltzmann suppressed. So as the temperature falls, electrons and positrons become exponentially suppressed by this factor. And in order then to describe the neutrino distribution in more detail, you need to solve this kind of Boltzmann equation where we have a time derivative, we have a term that accounts for the expansion of the universe, and we have a collision term. And the collision term comes with a few different components. There's some phase-space integrals. There are energy and momentum conservation. There's a matrix element that accounts for the strength of the interaction. And then there are all the different distribution functions, where the first two here corresponds to particle 3 and 4, combining and producing particle 1. And the last term here corresponds to particle 1 and 2, combining and therefore removing a particle 1. So that explains the signs that you have on these two terms. And then the other terms here, those and those, are Pauli blocking factors that you need to include in order to get the correct statistics in the end. So this can also be implemented numerically, and you can solve it. And in the end, it turns out that the correction is now minus 0.005. So we're getting towards the small corrections now, really. The next item on the list is another finite temperature QED correction that I will skip. And then we get to flavor oscillations, which I like quite a lot. And there is some interesting phenomenology, so I'll tell you a bit more about that. So if you recall flavor oscillations, we've heard about them quite a few times. So very briefly, they can be described with a density matrix. And if you have a density matrix and you want to describe neutrino oscillations, it's usually done with this kind of von Neumann equation, where the Hamiltonian is some effective Hamiltonian that we have seen for the vacuum case, has this form. This is entirely equivalent to the Schrödinger-like equation that we have also seen a few times, where we have a wave function and the same Hamiltonian. And then the relationship between the wave function and the density matrix is as simple as this. So you just take the outer product of the wave function with itself, basically. And then you get the density matrix. Yeah, and of course, the result, whether you solve the von Neumann equation or the Schrödinger equation, is that you get vacuum oscillations, which have been measured very nicely, for example, by Cameron. So if we then want to take neutrino oscillations to the early universe, we need, of course, to combine this with the Boltzmann equation. And then one could think, okay, how do we do that? And in the end, we just take them and stick them together. So we have the time derivative on the left-hand side. We have the effect from the Hubble expansion. Then we just stick on the oscillation term here, and we have the collision term from the Boltzmann equation. This can, of course, be done much more rigorously in several different approaches, but effectively, the result is that you just stick things together. And then, of course, since we now have density matrices rather than just distribution functions, there are some details of the collision term that become a lot more complicated. The Hamiltonian that is relevant in the early universe is the one that I'm showing here. So we have the vacuum term that you know and love. Then we have the asymmetric neutrino-neutrino term, and that is also the one that is relevant for supernova neutrinos and collective oscillations. And it's quite equivalent to the MSW term that you saw in Joachim's lectures also. And then there's also a symmetric matter term. So the MSW term itself is 0 because in the early universe, we have equal amounts of neutrinos, of electrons and of positrons. And electrons and positrons cancel out each other. So the MSW term is neglected. Instead, we have this term, which depends on the energy density of the electron and positrons and the pressure of the electrons and positrons. And that comes in as a higher order term. You can see that we have to divide by the W mass. So intrinsically, it's smaller than the MSW term. So then what is the result? In general, oscillations have the effect that they move different neutrino flavors towards each other. So if we look at muon and tau neutrinos, then they only interact via the neutral current, and electron neutrinos also interact with the charged current interaction and electrons and positrons. That means that it's more efficient to produce electron neutrinos, and when electron neutrinos are then, some of the electron neutrinos are moved to muon and tau neutrinos, in the end, we produce slightly more neutrinos. So we expect oscillations to lead to higher ineffective, and that's also what is found. We have this tiny increase in ineffective. In the figure here, there is a parameter scan in the mixing angles and the mass squared differences. And the one that changes the most is the sine squared theta 1, 2, so the red one here. And it's measured to be within the light red region here. But you can see that it changes a little bit depending on which end it is actually in. And that's part of the uncertainty that you in the end have on ineffective. The limitation of this calculation is that the neutrino-neutrino term here, this one, is not included. The reason is that it makes the calculation quite a bit harder. And when you include the full collision term as is done in this calculation, you're already spending quite a lot of computational resources. But it's interesting to see how much it can change the results. So we did a calculation where we used an approximated version of the collision term and then included the full neutrino part of the Hamiltonian here as well. That also means that this calculation is not as precise as the other one because we do not have the full collision term, so we are not doing as good a calculation in that respect. What you can see here is that in an isotropic universe, the normal mass ordering do not show much oscillations. The outer line here is the no oscillation result, and then for inverted mass ordering, we see a bit more oscillations. But it turns out that breaking isotropy can change these results. So if I can try to illustrate it with a bit of gymnastics. So if we assume that we have an isotropic solution, then we force our modes to do like this. But then if we allow the system to break isotropy, we can also have a mode that do like this instead. So we are basically allowing for different kinds of solutions that we are artificially removing by assuming isotropy. And that's also what we see. We set up a simple model here where we just have neutrino 1 moving in one direction, neutrino 2 moving in a different direction. And then the result is that for normal mass ordering, we see much more flavor oscillations. And we also see that neutrinos moving in direction 1 and direction 2, they have different number densities. I mean, the numbers are small, of course, if you look at the y-axis, but it's quite interesting that we actually introduce a spontaneous anisotropy in this way through neutrino oscillations. For inverted mass ordering, nothing much is happening because that is really the isotropic solution that is the right one here. So the change is not noticeable. We also find that within this model, there's a small change to delta ineffective. It's still on the order of these 0.0005, so it's tiny. But nonetheless, it means that the number here could change on the last digit when these neutrino oscillations are included as well. So beyond standard model scenarios, we've heard a bit about sterile neutrinos. There are also low temperature reheating and large lepton asymmetries that are interesting scenarios. So regarding the sterile neutrinos that Joachim talked about, I would like to put a bit of perspective. So I've taken one of the, it's slightly older, but one of the data combination figures global fits here for a 3+1 model. And this is for mixing between an electron flavor and a sterile neutrino. And then if we look at an effective and the contribution to an effective from a sterile neutrino, you can see that almost the blue box here corresponds to the blue box there. So almost all of this region will produce very large contributions to an effective. And from that point would be ruled out by cosmology, at least in the simplest model. There have been quite a large number of attempts to circumvent these limits. And it can be done with extended models, but you need to add some more wheels to get around it. And also there's the effect, of course, that if you have even a small abundance of a 1 eV sterile neutrino, for example, then it will contribute to the sum of the neutrino masses. So the limits that Olga was talking about there are also going to put further constraint on models. So with that, I would like to summarize. We have this ineffective that is a quite powerful probe, both of standard model physics and also of beyond standard model physics. The standard model value is this 3.044, and now you have seen how the corrections come from the relativistic approximation, assuming that the electron mass is 0, finite temperature QED effects, the non-instantaneous decoupling, and neutrino oscillations. And then I'd also like you to take away that neutrino oscillations in the early universe can break both isotropy, and we expect them also to break homogeneity, but we have not seen that in a full numerical setup. And of course, finally, ineffective is also a probe of, for example, sterile neutrinos. So, thanks.
Thank you, Rasmus. Other questions? I had one technical question when you do these finite temperature. No, sorry, this was the QED corrections.
Yeah.
So you had like first order, second order, third order.
Yeah.
What is the order here? What's the order?
Sorry, the order is in the elementary charge, electric charge. Yeah.
Okay, so like this standard exponent, so like alpha.
Yeah, so they use E in these calculations, okay. and not alpha. Okay. So there would be some factor difference, I think.
But you had some of these ring diagrams that had like multiple insertions. Is this not like a higher order collection?
Okay, so I'm not an expert on the details of this calculation, but here. So the reason that the dots are here is that it's a summation of an infinite series, and the dots here are photon self-energy that they put into the diagrams.
Okay. There's a question online. Yeah, if there's a question online, maybe this person can unmute and ask the question.
Yep. Yeah. Have you considered the Dirac or the Majorana nature of the neutrino in any of your term? Do you think it's reasonable?
So the question is if I haven't considered the Dirac or Majorana nature of the neutrino?
Yes.
Yes. So at this level, I do not think it's relevant. Yes. The neutrinos are ultra relativistic, and any sterile or right-handed modes that would be there in the Dirac case are not excited. So from this point of view, the calculation would be the same for Dirac and for Majorana neutrinos.
Okay, thanks.
Another question here.
Can you talk about the symmetric potential again?
A little bit more, yeah. Sorry, wrong way. So this one, right?
No,
the blue one down here. Yeah, so the point is that since we have a plasma, there are corrections to the propagator, and when you include that correction, you get this kind of terms.
So this comes from finite temperature.
Yes, that's a finite temperature effect.
Okay, thanks.
Other question?
As far as I could see it, you considered only quite light sterile neutrinos in their effect on an effective. Up to which mass do they contribute, and where do they become too heavy at some point?
So it depends on when you measure an effective. So an effective is the number of relativistic degrees of freedom. So if you measure an effective at BBN, you'll need something that is relativistic at 100 keV and a bit below. So the limit would be a bit below that. If you consider an effective at the epoch of CMB, the temperature is much lower. And even I think some of the EV sterile neutrinos start to become non-relativistic, and the effect is a bit more convoluted now. Yeah.
Thanks.
But at 1 MeV?
Sorry?
At 1 MeV, where the neutrino decoupling is happening? Like the considering...
At 1 MeV?
Yeah.
Sorry, what is the full question?
No, so yeah, considering sterile neutrinos here, right after neutrino decoupling, how much effect does it? No, I'm just asking in general, how much effect? Yeah. No, but even at keV, how much effect does it have on the N effector?
I mean, it depends on the mixing angle with the
Yeah. Yeah, this one. So since it's m squared, you would have, this is basically KV neutrinos. And then this calculation is not very accurate because we do not include muons and pions.
Yeah.
But as a rule of thumb, it still holds. I mean, the contours will move a bit, but both scales are logarithmic, so it takes a lot to move them by much.
Yeah, okay.
Yes.
In that work,
Yes.
that mixing angle is largest of the mixing angles you have with the usual neutrinos, or?
That depends. So the question was in this figure, if this is the largest mixing angle we have.
No, so like the theta in the x-axis.
Yeah. So in this calculation, I'm assuming that only the mixing angle between sterile neutrinos and electron neutrinos is non-zero.
Okay.
So
But
on top of that, you could have.
Would it make a difference if you choose a different angle, or would it just be the same?
If you choose a different.
I think like would it make any difference if you say, okay, they couple with the muon neutrinos there?
It makes a bit of a difference, but not a huge one. If you have both of them non-zero, then I mean, again, you can move the contours a bit, but not that much. Okay. And if you have mixing angles between several of the active neutrinos and the sterile, of course, it adds up.
Yeah. All right. Thank you.
If there are no further questions, then thank you very much, Rasmus.